You guys know that? Okay, so here's what, that's pretty good. What I figured I would do next is just go a little bit over the uniform PDF. Have you guys done the uniform PDF recently? In this course, gone over it? If I put up a picture in recitation, if I put up this picture here, so the x is the domain of this function. The y is the probability mass, or the probability density here, I should say. And can anyone, so this look familiar to everyone? This is uniform, or uniform probability density function is simply one where there are some events which have the highest possible probability and everything else is zero probability. Fair enough? Now, can I ask someone to fill in what the, I've said here that from 0 to A, there is maximal probability, and everything after A is 0. Can I ask someone to tell me what the question mark there is going to be, what the value there should be? Okay. Everybody sure why it should be 1 over A? Yeah? Someone want to tell me? Okay, all right. Okay, the probability function was one of the rules that we've done, a probability density function and a probability mass function. When we add up the values of the probabilities, when you add up the function values over the entire domain, it has to sum to 1. So the probability of all events has to add up to 1. So if you look here, right, A times 1 over A, we want this area under this curve to be 1. Perfect. Now, one exercise I was going to ask you guys to help me go through here is that to make sure that we know that when there's a probability density function we have, firstly, I've given you a picture. Now, I want us to be able to write that down as an expression, what that is, and then use that expression to derive the expected value and the variance of that. So what I'm going to do is I'm going to just write out here what the PDF is, and I'm going to ask for a volunteer just to go over the expected value and then someone else to do the variance. And simply as an exercise that, once you start manipulating the algebra of probabilities, it's just empowering. We're not going to use this for anything, but you'll know, just I want to make sure everyone knows how to write down a probability function and do a simple integral. See, this is the probability function here. So here I've done the easy part. Someone want to come up here and figure out here how would we go about doing the expected value. We have a probability density function here. This over here. Oh, thank you. All right. What I'd like to do is go from here. Now we don't need the picture anymore. Say, how would we derive the expected value of x? I will get you colored chalk. Okay. Any volunteers? Anyone? All right. We'll save the variance for you. Okay. Just want you guys to be able to do this because we'll definitely put something on the exam here, so you need to pay attention. See, I have my motivational tactics shot.
0
to
A.
Okay.
1 over A times X.
Okay, could you tell me what, so just for the benefit of the folks who phased out on this when we did it, when we did it in recitation, could you talk about what you're doing?
So we're weighing each possible outcome of X, which is uniformly distributed from 0 to A by its probability mass,
right,
which is uniform 1 over A.
Right.
So
yeah,
this is a pretty easy integral to do. So we can do it in exact form. So that's 0 to A of x squared 2A. So that's A squared over 2A, so that's A over 2.
okay, right, thank you. Just want to remind guys here if, I'm sorry, I didn't catch your name. Jeff? So what Jeff did here was he just wrote down this expression, and just want to make sure I've written this one down at least once. The expected value is probability of x times x dx integrated over the whole domain. So he didn't pick this out of nowhere. You know, if you just write down this expression, so you write down probability of x multiplied by x and integrate it over the domain, you should be able to work this out for any probability expression. Okay? So if you think about it, that this is giving you, an answer that you could have just looked off the picture here also, right? What is the mean value of this 0 to a? It's half of a. Okay. All right. Now, let's see. Anyone want to try? Well, someone has to try the variance. Okay. Okay.
So variance.
Just stand back, so I don't know how.
Calculate with the expected value of x squared minus the expected value of x squared.
Does everyone know where that expression on the right came from? Okay. I'm sorry, you went over it? That was in recitation?
No,
was that in lecture? Okay.
Sort of.
Hey, Raj felt terrible about that. So.
Integral from 0 to 1 over a of
yeah.
0 to a of 1 over a.
Yeah.
X squared dx equals x. A squared over 3 minus, it was
1 over a.
2, yeah.
Yeah. Oh, yeah, that's right.
So
Over 2.
minus a squared over 4 is
A squared over 12. Right.
yeah.
Okay. Great. Does anyone have any questions about this, including where the first variance came from? I know everyone nodded, but because this is something you've got to be very comfortable doing from point of view of your general probability knowledge and the exam, is that being able to express the variance in terms of the second and the first moments. That's what these terms are called. The expected value of x, that's the first moment. Okay, if that term ever comes up, expected value of x over PDF is the first moment of that PDF. Expected value of x squared is the second moment. Expected value of x minus the mean squared, that's the variance. That's called a second central moment. Okay, so there are moments and central moments. These are additional terms you're going to hear about when, if someone decides to have a conversation about PDFs with you. And but the variance is the difference between the second and the square of the first moment, not the and the variance itself is the second central moment. Just buzzwords. Okay? Any questions at this stage? Okay, I want you guys to be able to do this. Well, I said the exam stuff, but also in MATLAB we're going to write a routine that you'll be able, in which you're going to need to compute the different parameters of a uniform distribution as well as being able to plot it. Okay, so I want you to be comfortable with being able to manipulate these symbols, because you're actually going to be writing code with that. Okay, all right. Here comes the second and the last PDF. This is the one we're actually going to be using a lot in the lab. So finally we get to something that's relevant for the lab here. You guys have all seen the Gaussian PDF, the picture for it. All right. And as I mentioned before, a natural, I'll ignore the y-axis, the y on the x-axis. It's supposed to be an x. And the reason I'm introducing a Gaussian PDF here is very simply because it makes sense to model MR intensities as Gaussian random variables. For the reasons we talked about before, there's thermal noise in the MR imaging process. In contrast to CT imaging process, the uniform distribution that I showed you before actually represents pixel values in a CT, in a CAT scan. It's computer-assisted tomography. That's an X-ray based imaging technology where it's much more, you can say with a lot of confidence that intensity value 204 represents bone across all patients.